One incredible device has made us look again at everything in the night sky. It shows the heavens in stunning clarity. It captures the birth of planets and the death of stars. It transports us back to the dawn of time to witness the creation of the cosmos. The Hubble Space Telescope has revolutionized the way we look and think about the universe and our place in it. This is the Cat's Eye Nebula. It's over 27,000 trillion kilometers from Earth. But we see its astonishing beauty thanks to one extraordinary telescope, Hubble. A giant gas cloud appears in breathtaking detail. We track the weather on Mars and study the atmosphere of a planet 150 light years from Earth. Hubble shows us the universe in a new light.
Hubble is the flagship of our fleet, plain and simple.
Mankind has always been fascinated by the stars above, and the world's greatest telescope delivers them in revolutionary clarity because it's in orbit 480 kilometers above us, free from all the distortion of Earth. When a distant star emits a beam of light, it launches it on a journey across unimaginable distances. The light travels at 300,000 kilometers a second across the cold, clean clarity of space. For 12 billion years, it can hurtle towards a final target, our eyes. But in the last 500th of a second, the light slams straight into Earth's atmosphere. Above our heads, the air disrupts the passage of starlight. We see the distortion every time we gaze up at the night sky. The stars themselves don't twinkle. It's the air. Mountain air is thinner, drier, cleaner, so telescopes on lofty peaks can get a crisper image, but they're still not high enough. To truly see the stars in crystal clarity, to try to define the size and age of the universe, scientists need a whole new type of telescope. One far above the smog, the dust, and the air itself.
It was clear to the entire astronomical community that to make progress in that field, it was necessary to go to space.
A giant telescope in orbit will capture the light fresh from the stars themselves. It will also test the limits of earthbound engineering. Dominic Tenerelli is there from the start.
There were several of us who took it as a personal responsibility to make sure that we were going to provide the finest telescope that had ever been built.
Hubble is one of the 20th century's greatest feats of engineering. The final design combines 400,000 components and 45,000 kilometers of wiring in a telescope the size of a bus.
It was going to be one of the largest telescopes that we had on the planet, but only now flying above the clouds.
Lockheed's Jim Crocker remembers the key challenges Hubble's engineers had to tackle.
How good the optics are, how big the optics are, and how stable you can hold them. Those three things really set the limit to what Hubble could accomplish.
The first major design hurdle is the mirrors at the telescope's core. Hubble is a reflecting telescope. It collects photons of light from distant stars using a giant concave mirror. The light gathered by the first mirror then bounces onto a second, smaller convex one. This in turn reflects it back through a hole to form a focused, bright image. Constructing these light-collecting optics is a Herculean task. It takes engineers 4 million man-hours to design and build the mirrors.
The optics were the heart of the telescope. Everything depended on the quality of the optics and the preciseness of its prescription.
The mirror's weight must be kept to a minimum, so they set the glass in a sandwiched honeycomb structure. This drops the weight from 3,600 kilos to 800 kilos, but keeps it strong enough to withstand blastoff. For extra precision, they shaped the 2.4-meter wide main mirror using a pioneering computer-controlled rig. The rig carefully polishes the block of glass into the smoothest large surface ever made. If the mirror was the size of North America, the tallest bumps on its surface would be just inches high. The telescope will sit above Earth's murky atmosphere, allowing the precise mirror to make a quantum leap in observing power. Once Hubble is launched, it will reveal 100 times more detail than giant ground-based telescopes. But that precision will be wasted if the space telescope itself isn't held rock steady.
If you think about it, when you hold your camera, the camera has to be very still when you take a picture so it doesn't blur. And if you have a big telephoto lens on the front of the camera, you have to be even more stable in holding it.
The design team turns to a high-grade substance to achieve maximum stability: graphite epoxy. They use it for the struts and supports that hold Hubble's mirrors in place. When Hubble was designed, graphite epoxy was cutting edge in space engineering. Today you'll find it in many tennis rackets and golf clubs. The rigidity and lightness that make it ideal for sports are also key to Hubble. But graphite epoxy's real value lies in how it reacts to temperature changes. In orbit, Hubble travels in and out of the Earth's shadow 16 times a day. As it does, so the temperature changes by more than 37 degrees Celsius. Most materials expand or contract when heated or cooled. But the graphite epoxy structure will deform by only 1/13 of the amount that a steel version would. It will hardly warp or flex, and so will keep the mirrors perfectly aligned. For added protection, the entire telescope is wrapped in reflective thermal blankets and dotted with 800 built-in heaters. They will keep Hubble's core within 1 degree of room temperature.
As you go from day to night, these heaters turn on and off to control the temperature very, very accurately.
The final challenge is to make sure that Hubble actually works. Finding the right star in the night sky using a powerful telescope in orbit makes finding a needle in a haystack look like child's play. It's like looking for one particular window with a high-powered zoom lens. If you can't see the wider picture, you have no way of knowing if you're even looking in the right area. So the designers equip Hubble's guidance computer with a map of 15 million guide stars. Razor-sharp ridges inside the telescope tube will block any stray light from the sun, Earth, or Moon. This means that only light from the celestial targets will reach the cameras and other instruments behind the main mirror. Each element of Hubble's design needs to work flawlessly for it to succeed. The telescope's prime goal is to build on the work of the man it's named after, Edwin Hubble. He launched a revolution in astronomy and continues to inspire modern scientists, such as the Carnegie Institute's Wendy Friedman.
Edwin Hubble was no doubt the greatest astronomer of the 20th century, one of the most remarkable astronomers of all time.
In the 1920s, Hubble carefully measured the huge distances of space using giant telescopes in California, and his results shocked the world. There were other galaxies outside the Milky Way, and almost all of them were flying away from us. Hubble discovered that the universe was bigger than anyone had thought, and was getting even larger.
Hubble's breakthrough was enormously revolutionary. It completely changed the perception of the universe that we live in.
But even using the largest telescopes on Earth, Hubble couldn't measure the exact size and age of the universe. Now, decades later, his mechanical namesake will pick up where he left off.
CDR Houston, good morning, Lauren, you're loud and clear.
April the 24th, 1990. The Space Shuttle Discovery stands on the launch pad. Aboard is the Hubble Space Telescope. Not including the launch itself, the Hubble has cost $2 billion to design and build. All that money, almost 2 decades of hard work, and countless reputations depend upon the Space Telescope being a success.
5, 4, 3, 2, 1, and liftoff.
Discovery blasts off and carries Hubble 600 kilometers up. The shuttle bay doors open. The communication dishes deploy. The solar panels unfurl. The shuttle gently lets go and powers away. Hubble is in orbit. Finally, after weeks of testing, the telescope takes its first image.
That was a joy. That was a joy to see first light. We had a telescope up there.
The shot isn't beautiful, just 2 lonely stars. It looks promising, but the elation doesn't last long.
Now, within 24 hours, we knew we had a problem.
Instead of pinpricks of light, the stars are fuzzy. Detailed analysis shows that even above the atmosphere, there's still something blurring the images.
I think we were so stunned, we really didn't realize at first the extent of the problem.
The images are out of focus, and the cause is devastatingly simple. Hubble is short-sighted.
The conclusion we've come to from that is that there's a significant spherical aberration that appears to be present in the optics.
The vast primary concave mirror is too flat. Its outer edge is 2 microns lower than it should be.
The mirror was ground a little too much away on the edges, about the thickness of 1/20th of a human hair. Now that doesn't sound like much, but in optical terms, it was enormous.
How could this have happened? Engineers discover that a piece of mirror testing equipment had been wrongly assembled. One humble washer in the wrong place has wrecked Hubble's accuracy. Hubble is not just short-sighted, it's also shaky. The solar panels are unstable. Every time Hubble passes from day into night, the temperature change causes them to flex, jolting the entire satellite. Hubble is in crisis. The optics and the stability are both seriously flawed.
It was just devastating to have worked so long on something and then see your hope shattered.
Some science is still possible. Computers clean up some of the images. But the detailed astronomy that the Space Telescope has been built for will not be possible. Hubble's primary mission, the grand survey of the size and age of the universe, cannot even be attempted.
For our own project, which was called the Hubble Key Project, to measure the distance scale, it was almost a complete disaster.
People can make mistakes. But when you found out the history of the problem, that's when you got angry.
Overnight, Hubble goes from being science's next big thing to astronomy's techno-turkey.
Coming on the heels, if you will, of the Challenger accident, it looked like NASA had lost the right stuff.
NASA must fix Hubble. A team of astronauts will have to travel up to the telescope and attempt to repair in orbit. They need to fit a series of lenses or mirrors that will cancel out the flaw in the main mirror. They should work like a pair of glasses for Hubble.
It sounds simple, putting glasses on something, but these glasses were very, very difficult to build. The lenses were the size of nickels, dimes, and quarters, and they had a very unusual shape. It's called an anamorphic asphere on a toroidal blank. What that means is they look like potato chips.
4 contractors race to produce the lenses. Only one succeeds. But there is still the problem of how to fit them. The razor-sharp ridges inside Hubble mean that astronauts cannot enter the telescope tube. Then Crocker has a eureka moment while visiting colleagues in Germany.
I was taking a shower, and in Germany, they have these showers that are on a rod. And so I slid it up and basically put it in position, and then I realized what the fix could be.
Like the showerhead, a system of rods could slide the lenses into position. A robotic arm would then angle them into the correct alignment. With the corrective device in construction, NASA assembles an elite team of astronauts to install it in Hubble. It includes spacewalk specialist Jeff Hoffman. The pressure is intense.
We were told face-to-face by the NASA administrator at the time, who said, you know, that's the only thing that I want to tell you guys before you go up for your mission. Fix Hubble.
The astronauts embark on 12 months of grueling training. Working alongside them is Hubble engineer Mike Weiss.
It was extremely challenging, probably the most challenging shuttle mission ever attempted. The agency had never attempted 5 back-to-back spacewalks. Never.
While the astronauts train, Weiss has to ensure that all the new hardware will survive the shock of a shuttle launch and the rigors of life in orbit. The men and machinery take on a barrage of tests.
We are standing in the middle of the envy of every teenager in the world, a giant acoustic test facility. We take every piece of hardware that we fly, attach it to the floor, and with the speakers you see in this facility, hit it with 2 minutes of acoustic energy, about 150 decibels. The 2 minutes is what it sees in flight.
There were many different types of training. For the spacewalks, certainly the most important is the underwater training tank. We were doing some very, very fine work. I mean fine in the sense of Swiss clockmakers type of fine, which is not easy in a spacesuit.
We are looking at a very, very large thermal vacuum facility. The thermal vacuum facility is where we put our hardware, pull a vacuum on it, cool it down, heat it up, make sure it can survive those harsh environments that it sees in space.
We got incredible cooperation from everybody, much more so than in a typical mission. Everybody was working together on it. Everybody was rooting for us.
This is our centrifuge test facility. Basically what we do is we hang the payload off the other end, spin it up, develop the acceleration loads that we'd see in flight, and just prove that we can survive that type of environment. If we needed to, we could develop 30 Gs.
For a full year, the team and the equipment are put through their paces. There will be no second chances on this mission.
This was a very intense training period, and it's what you sign up for. It really made us a very tight-knit group.
On December the 2nd, 1993, the crew boards the shuttle Endeavour. The world watches as they blast off towards the stricken Hubble.
Okay, it's daylight outside, so you might want to put your visors down.
Each of the 5 spacewalks tackles a set task: to carry out maintenance work, to replace the faulty solar panels, and to install new instruments.
Okay, here we go.
Working in spacesuits and zero gravity isn't easy. But there are some upsides.
We were moving around pieces of equipment the size and the shape of a grand piano. No way could I have moved that around on the Earth. You know, you feel like Superman up there.
They fit the new correction device successfully. But not everything goes smoothly. One of the faulty solar panels is too warped to roll back into its original holder. The astronauts jettison it into space.
It started to somersault, and we were just mesmerized. It was flapping, you know, it was like the wings of some giant prehistoric bird.
But the most challenging surprise comes as Hoffman tries to close one of Hubble's equipment bay doors.
It's not closing, the doors aren't closing right. Like if I'm just doing it at the top, I can get them to come together.
This was something we had done dozens of times underwater, but when I went to close them, it didn't close right.
The effects of zero gravity have deformed the door. If it isn't shut, the telescope won't be optically sealed. All future observations will be ruined.
It was a potentially fatal problem. You'll basically lose the telescope.
Another astronaut joins Hoffman at the door. Between them, they can hold it closed, but then neither has a free hand to lock it shut.
And we came up with an idea of adapting one of our tools in a completely non-standard manner, but basically to work as an extra hand.
Their plan is to hold the door shut with a strapping device, leaving them free to close the locks. They suggest the idea to ground control.
I think they had visions of us wrapping this tool all the way around Hubble and cinching it down, and Hubble was going to collapse like an aluminum beer can. Finally, the flight director, I think, made a good call. He said, look, team, we sent these people up. They can see better than we can. Let's let them go ahead and do what they think needs to be done.
The plan works. Mental ingenuity and some old-fashioned elbow grease get the door sealed. Hoffman's team returns to the shuttle. At 7 hours and 54 minutes, it clocks in as the second longest spacewalk in history.
That's just a spectacular vantage point. You're floating in the middle of nowhere, 50 feet above the shuttle, 400 miles above the Earth, sort of hanging between heaven and earth, so to speak. That's something I'll never forget.
After 12 months of preparation and 11 dramatic days in space, Hoffman and his team accomplished their mission. The focus now shifts to the lenses of the correction device itself. As Endeavour touches down in Florida, the engineers at Hubble headquarters prepare to take the make-or-break test image. December the 13th, 1993. The astronauts who have installed a correction device on the flawed Hubble telescope return to Earth. Their work is done. Now everyone waits for Hubble to beam down a test image.
We had been told by everyone in the press that what we were doing was impossible. But when we did finally get the optics aligned and took a look at the first image, we were all stunned. They were better than we expected. They were better than we hoped. They were perfect.
The mood was elation. Hubble had been fixed.
The trouble with Hubble is over.
The improvement is startling. All distortion is gone. The focus is perfect. Hubble begins unveiling celestial objects in breathtaking detail.
The images that came down were spectacular. Distant galaxies, star formation regions. Nothing like that had ever been seen. It was incredibly exciting.
The stability problem is also gone. Hubble is so steady that if the telescope were in Manhattan, it could keep a laser beam locked on a dime nearly 320 kilometers away in Boston.
Well, now we knew we had a telescope up there that would perform how we originally wanted it to perform.
The optics are performing perfectly, and Hubble's instruments start capturing flawless data. Hubble carries 2 cameras and 2 spectrographs. Each is designed for a specific type of observation. Since launch, Hubble has beamed down enough scientific data from these instruments to fill over 40,000 compact discs. Scientists around the world have used this information to transform the science of astronomy. Objects that have now been studied for hundreds, if not thousands of years, are now seen in a new light. One of Hubble's greatest hits comes just months after the successful repair mission. Astronomers know a comet is about to crash into Jupiter. They point Hubble at the planet, prime it to capture the collision, and wait for the crash. Astrophysicist Mario Livio watches the historic event live. This is the first time anyone will witness a collision in space.
Hubble really gave us a ringside view of that event. For us to have Hubble at the right time to watch that was extraordinarily exciting. And we could actually see the plumes as they were coming up in the atmosphere.
The comet strikes with 600 times the force of the world's entire nuclear arsenal. And this event was taking place in Hubble's backyard. Jupiter is over 750 million kilometers from Earth. The light it emits takes around 45 minutes to reach us, but when Hubble looks at another star on the other side of our galaxy, the light has taken thousands of years. When it looks at another galaxy on the other side of the universe, the light has traveled for billions of years to reach us. That's probably just as well, because there are objects out there in space that if they were closer would destroy us in an instant. Black holes. These were massive stars that collapsed in on themselves as a result of their own gravity. They devour everything in their path, even light itself. So how can Hubble see something that is totally black?
Hubble really does not see a black hole. You see the effects of the black hole on its surroundings. For example, we would see the disk of matter that is around that black hole. Or sometimes the presence of the black hole there would modify the orbits of the stars around it.
If a giant black hole was bearing down on Earth, there would be nothing we could do to stop it. The void would swallow the sun and all its planets whole, us included. Thankfully, even in the vast reaches of space, such things are still rare. It takes the sheer power of Hubble to spot them within the cosmos. And it can also study less destructive objects that might make us rethink our place in the universe. Planets orbiting distant stars that might hold the ingredients needed for life. David Charbonneau explores one of them, known by the catchy little name of HD 2094-58b. In 1999, Charbonneau is still only a student at Harvard when he starts studying the gassy planet using a tiny telescope set up in a parking lot.
It was only 4 inches in diameter. You could have bundled the entire observatory up and put it in the trunk of your car.
The small telescope reveals that this planet's orbit carries it between its star and Earth. This means that starlight passes through its atmosphere, opening it up for further tests. But Charbonneau's ground telescope wasn't up to this sort of work. In fact, the only device that could do the tests was the mighty Hubble.
That was a huge shift to go from the little 4-inch telescope in a woodshed to the Hubble Space Telescope, which is possibly the most powerful observatory that astronomers have ever built.
Charbonneau uses a Hubble instrument called the STIS spectrograph to detect what chemicals are in the planet's atmosphere. Like a prism, the spectrograph breaks down the light that has passed through the atmosphere into its constituent parts. Different substances emit different types of light. Each ray of light carries an imprint of the chemicals it has come from and passed through. And you may not realize it, but you see the way substances affect light every firework night.
If you've ever been to a fireworks display, you might wait for a rocket to go up, and then you'll see this very distinct color of light. And that particular color of light, whether it's that particular green or red or white or blue, points to a particular chemical that's been used in the contents of that rocket. And so when you see that color of light, then you can figure out what chemical you're dealing with.
Chemicals also absorb light, the same color they emit. The atmosphere around Charbonneau's planet absorbs a particular shade of the color yellow, which means there is sodium present. Follow-up Hubble studies showed that the atmosphere also contains carbon, oxygen, and perhaps even water, the vital ingredients for life as we know it. But the planet is heated to a scorching 815 degrees Celsius. It seems an unlikely candidate for an alien homeworld.
The Hubble is really in a class all its own in terms of being able to focus in and study the atmospheres of these very exotic extrasolar planets.
In an area of space called the Orion Nebula, Hubble can see how planets are formed. The nebula is a giant gas cloud 30 light-years across, and inside it hundreds of stars are being born. Disks of gas swirl around some of the stars. Inside the disks float tiny dust grains, grains that may one day clump together into a fledgling planet. Henry Throop of the Southwest Research Institute needs Hubble to test this theory.
I was particularly interested in whether you could see the first stages of planet formation in the outer edges of these disks. We're looking at formation of planets. We're looking at answering the question of how unique we are.
Conventional ground-based telescopes can hardly make the disks out. But the extremely high-resolution ACS camera on Hubble can see them clearly. By tracking how the disks affect starlight, Throop can study the dust grains inside them.
We can tell the difference in the grain size by how the light passes through them.
The effect the dust grains have on starlight is the same as foam blocks on water waves.
Now you can see these waves coming out in the water. Over here, they're radiating outward in much the same way that the light from the Orion Nebula is coming out. These blocks represent the dust grains in Orion, and we're going to send the light waves through, just like the light in Orion gets sent through the dust. Now what you can see here is the light, the waves, are traveling through the dust grains, the blocks here, and going outward, so we can see the waves as if they weren't blocked by anything.
Throop believes larger particles will have a different effect.
Now what you see here is these dust grains are blocking the light much more than the small grains were. It's just not transmitted through nearly as strongly. And that's exactly the same thing that we're seeing up in Orion.
Up in space, Hubble sees the changing effect on the light as changes in color. Normally, the starlight coming through the dust appears red. That's because the dust grains block the red light less than the other colors. Its long wavelength means it can wriggle through. But the disks in Orion appear gray to Hubble. This means that dust grains are getting bigger and blocking all of the light. One day, the grains in the disk may snowball into other planets, perhaps even one like Earth.
Now, but it's really the big question here. Are we unique? Is the Earth unique? Is the solar system unique? And where do we fit in?
Ultimately, Hubble reminds us that Earth is just one tiny planet floating in the enormous reaches of space. But the pioneering telescope can also transport us back in time, back to the dawn of the universe itself. The Hubble telescope works like a time machine. The starlight it sees has taken millions, sometimes billions of years to reach us. The events themselves happened before man had even evolved. The deeper into space Hubble searches, the further back in time it travels, and the fainter the stars and galaxies appear. This poses a big question. Just how far back can Hubble see? Dr. Henry Ferguson's team decided to find out.
These galaxies that we're seeing at the far distant reaches of the universe are very, very faint. And some of the faintest ones that we're seeing about 1 photon per week striking the human eye. So there's very, very few photons of light reaching us. And it just takes a lot of effort to collect that much light.
There's no chance of seeing these galaxies in the night sky. Even Hubble struggles to pick out their dim light. To overcome the challenge, the team develops an innovative use for the Space Telescope. It's called a deep field, and it works just like photographing stars in the city.
Taking the Hubble Deep Field is very much like trying to take a time exposure with a normal camera. You could just click the shutter and you wouldn't see anything because you haven't let light get in for very long. If you want more light, you probably need more time.
When you leave the camera's shutter open for a whole minute, it can collect and build the faint starlight into an image.
Now, if you do that in a city with lots of bright lights around you, in the final image you might see a few dozen stars. If you get out to a cold mountain top, you'll see a lot of stars. And if you do it with a big telescope, you'll start to see distant galaxies.
The deep field plan is inventive but risky. Over a week of Hubble's highly sought-after time will be spent taking images of one blank, boring spot in the sky. The team picks a dark area with no bright nearby stars. They have to avoid anything that would mask the dim light coming from distant galaxies. But no one really knows what they're going to find out there.
There was very much a sense of fishing with the Hubble Deep Field. It's just not obvious what you're going to find.
Over 10 days, Hubble takes more than 300 images of a single spot in the sky. Each only captures minute traces of light. But layer one on top of another, and empty space soon fills up.
On one snowy morning when the people were able to finally gather around a computer screen and put up the images, that was extremely exciting.
It might not be one of Hubble's prettiest pictures, but its contents make it one of the most mind-blowing.
The slice of sky that you're seeing in the Hubble Deep Field is about the size of a grain of sand held at arm's length. It's this tiny, tiny spot on the sky. And yet when you blow that up with a telescope like Hubble, there are 3,000 galaxies in that tiny grain of sand. Each galaxy has anywhere from 1 billion to 100 billion stars in it.
Every slither of the sky contains this vast profusion of early galaxies. They're nothing like our own galaxy, yet cosmologists believe that they eventually combined to produce galaxies like our Milky Way. Subsequent deep field surveys probe even further back. The deepest so far is the ultra-deep field. It combines 800 individual shots onto one image, twice as many as the original deep field. Its final image reveals the universe's oldest stars, 13 billion light-years from Earth, about 2 billion further than the first deep field. Ancient stars like these forged the matter that makes up Earth and us humans. But Hubble's most startling data finally allows us to close in on the event that created all matter in the universe, the Big Bang. Ever since that titanic explosion, all the structures and galaxies of the universe have been flying apart. Measure how fast, and you can track back to the moment the universe began. This was scientist Edwin Hubble's dream back in the 1930s. Now Wendy Friedman can get precise results using the telescope named in his honor. She measures the distances by studying one particular type of star called Cepheids. All Cepheid stars have standard brightness like street lamps. And like a string of street lamps, those which are close to us look bright. and those further away look dim. By measuring the brightness of a Cepheid star, you can calculate how far away it is. Friedman's team measures the brightness of 800 separate stars. She then calculates their relative speed and position. The results confirm that the universe is expanding. The galaxies are flying apart from one another. But if Friedman then plays this motion in reverse, she can calculate when all of the galaxies started out in one concentrated spot. An event we call the Big Bang.
Before the Hubble Space Telescope, we didn't know whether the universe was 10 billion years old or whether it was 20 billion years old. There was a factor of 2 discrepancy, and when you think of that, that's huge.
The Hubble's accuracy has allowed Friedman to calculate the date of the Big Bang. Time, the universe, and everything in it exploded into existence 13.7 billion years ago.
In terms of our understanding these questions of the expansion of the universe and its composition, the Hubble Space Telescope has been probably the most powerful tool we have ever had access to.
In dating the Big Bang, Hubble has achieved its greatest goal. Now it's tackling new challenges. One is a mysterious substance that's holding everything in the universe together. It's invisible, but Hubble is still able to find it. In the years since its launch, the Hubble telescope has achieved its main goal. It has let us calculate the age of the universe. But in the process, it has found substances that the scientists haven't even seen before. One new challenge is called dark matter. It's an unknown material that seems to be binding everything together. We can't see it and don't know what it's made of. But Richard Massey of the California Institute of Technology is using Hubble to study it.
Dark matter is kind of embarrassing, really. The fact that it sort of makes up the vast majority of the universe, but we still know absolutely nothing about it, is really rather embarrassing.
Despite this, the cosmologists are certain that dark matter must exist. If it didn't, galaxies like our own Milky Way would rip themselves apart.
So you can think of a galaxy rather like a pizza base. Both are spinning around, but they have something holding them together, keep all their parts in one place. In the case of the pizza, it's the stickiness of the dough that keeps it together. For the galaxy, it's the gravity of all of its different bits that hold it together. The problem is that when you look at your average galaxy, there doesn't seem to be enough matter in it to hold it together. Not enough matter and not enough gravity. So you'd expect it, when it starts spinning, to fall apart, just like a pizza base with holes in it. So a galaxy doesn't fall apart because there's an extra secret ingredient in there. And that's the dark matter. It's this additional mass that holds it all together.
Dark matter emits no light. It's invisible even to Hubble. But its gravity does bend the light from stars. Hubble can detect this bending. It's an effect called gravitational lensing, and it works like a magnifying glass.
Words seen through a magnifying glass appear slightly bigger, but also distorted at the edges. The lines which were straight curl up.
If you couldn't see the magnifying glass, you would still know it was there because it bends the letters. In the same way, Massey can detect the dark matter because it bends the starlight. He can see its distorting effect within some of the super high-resolution Hubble images.
A map of the dark matter actually looks very much like a sort of a map of a country seen at night from a satellite in orbit. You can just see the strings of lights lighting up along roads and highways. And in between that, there's these vast empty voids in the universe.
The dark matter plays a vital role in building the world we live in.
The dark matter forms, if you like, a scaffolding of structures, and it's crucial to the formation of stars and planets because the ordinary we're made can only form inside this dark matter scaffolding.
Hubble reveals where dark matter exists. And it will continue to discover more about this mysterious substance. It will do so with upgraded instruments. The team at Goddard Space Flight Center is testing a new set of hardware due to be installed on Hubble.
We keep sending astronauts back to Hubble because when we put a new instrument on this telescope, it's like a brand new telescope. It can be 10 times or 100 times more powerful than it was before.
This servicing mission will be Hubble's last. It's expected to keep working until about 2013, but eventually its systems will fail. It will slip out of orbit and plummet back down to Earth. By then, its successor, the James Webb Space Telescope, will have joined it in orbit. Its 21-foot main mirror will be almost 6 times the size of Hubble's, allowing it to detect even fainter objects. But even when the Hubble telescope is long gone, its legacy will live on.
When you're on a project like this, and you're so passionate about it, you give your heart and your soul and your life to the project.
One of the greatest thrills that I'll ever have was to touch Hubble with these hands, you know, in space. Doesn't get much better than that.
Hubble is one of the most important scientific instruments that has ever existed. And for some problems, it's the most important scientific instrument that has ever existed.
Hubble's supreme achievement has been to change the way we look at the night sky. Its images give us just an inkling of the scale and majesty of the heavens above. It has shown us distant planets and galaxies, found unknown matter and structures, and measured the age of the cosmos. It has changed our understanding of the universe and our place in it.